equation AX equal to XB problem, sensor calibration without correspondence. And the presentation is done by Ackerman.
Yes. Thank you, Mr. Chairman. Yes, this work is done by myself and Gregory, Chirikjian, who's also here. And we're looking at the AXXB problem, the AXXB sensor calibration problem. And we want to leverage some theory from probability theory, especially on leaf groups, to help solve this problem. And we're most concerned with this consideration here, which you'll also get in more detail, is solving the problem without this notion of correspondence. And so in outline of the talk, I'm going to tell you what the AXXB problem is, why it is important in practical applications. I'll go through some of the notation of the probability theory and leaf groups to kind of get everyone on the same page. We'll present the formulation of our probabilistic solution to the AXXB problem. We'll show how we chose to solve it in this instance, and then I'll give some concluding remarks. So the AXXB problem is a sensor calibration problem, and it's very common in many robot sensor type schemes. We find it in camera calibration, Cartesian robot calibration, hand-eye, aerial vehicle, in image-guided therapy, many different applications. And here we're dealing with the equation AX equals XB. X is the unknown, the value that we're searching for. A and B are two separate sensor measurements that we are trying to reconcile to get this value of X that is some descriptor of the system that we are working with. And oftentimes, or most of the time, the AXXB problem is a relative problem, and that's where its strengths lie. And so here's an example from image-guided therapy, an ultrasound system. You see here we have two ultrasound probes. Really, it's one probe in two different positions over a motion of time. Here you see an electromagnetic tracker, which is sensor number 1. And all of the B's correspond with that sensor. And here we have A's, which is the image from the ultrasound probe, the ultrasound image, and that's sensor 2. So all of the A's correspond with this sensor. And so you can see this loop right here is the loop we're concerned with, the AX equals XB problem. And we are looking for this description here. We want to know, how do you reconcile the image world, the image frame, with the three-dimensional world frame, so that we can do things like tomography and projections during ultrasound surgery. And how we get these values is not necessarily super important for our solution algorithm, but you can see here they are relative motions. So B is a relative motion of the probe, A is a relative motion of the image, and we get these from the multiplication of two sensor poses. So again, we have the AXXB problem, and so I kind of alluded to, we're talking about transformations, we're talking about poses in three-dimensional space, which means we're working on SE3, the special Euclidean group in 3 dimensions. Which is the semi-direct product of R3 and SO3. And of course, SO3 is the group of rotations. So R and SO3 such that R transpose is the identity, and the determinant of R is +1. This was discussed in the first talk, so I won't go much more into that. But here we're going to look at SE3 and elements of SE3 as being decomposed or made up of this rotation element from SO3 and a translation element T from R3. This 0 here is a row vector of zeros, of course. We made this 4 by 4 matrix. And so in these poses, in these transformations in three-dimensional space, we're looking at what is the rotation, what is the translation. And those two pieces of information give us this value of x. So what is the full information in three-dimensional space to get from our imaging world to our real world. And again, that's just the ultrasound problem, but you have many other applications of the problem. Air vehicles, you're trying to reconcile IMU data, inertial measurement data, with some integrated pose measurements from another sensor. So if we look at the problem, we look at AX equals XB for a single pair of a single A and a single B, a single pair, so a single sensor measurement from sensor 1, a single sensor measurement from sensor 2. We see that it's not possible to solve a unique solution. So if we decompose AX equals XB into two equations here, one of the rotation, one of the translation, and of course in SE3, the translation is coupled with rotation. We see that the rotation equation has one parameter solution set. But then we look at the translation equation, and we see this parameter here is rank 2, it's degenerate. And so that leaves us with two unspecified degrees of freedom, which means the solution space is a cylinder, and so it does not give us a unique solution. But what has been proven is that if you now take two sensor measurements, A1B1 and A2B2, then you can solve this equation and get a unique solution. And this unique solution is possible when certain constraints are followed. And so I list the three main constraints here. These I'm going to mention and leave for further questions or questions offline if you have them. But we're mainly focused on this one here. So the first two constraints that we have are the SE3 geometric invariants are satisfied between A and B, and pairs of A's and B's and another pair of A, B. And this is something that you can see defined in these works down here. We also have to have the angle of the rotation axis is sufficiently large, depending on your noise factor. But what we're concerned with, and what a lot of times is overlooked in this problem, is the correspondence of A-B pairs. And that's the question of, does A actually match up with B? And I'll explain a little bit more about that in a second. But what we see in traditional solutions is, given that most of the time these are not followed in the presence of noise, in the presence of real-world applications, we have to take more than two pairs of sensor measurements, more than two A's and B's, and concatenate a bunch of them and get a least squares solution to the problem. So going back to this issue of correspondence, what do we mean by correspondence? So if you remember the ultrasound application, we have two sensors, we have a tracker, and we have the ultrasound image, and we're getting data streaming from each of these sensors. And what we want is to know which A from sensor 1 matches which B from sensor 2. And so if you have a perfect system, of course you get both of these in at the same time, you can mark them and you're good to go. However, we don't have perfect systems, and so many times this notion of correspondence will be unknown, or we'll have pieces missing. And so we can see that these incoming data streams can be presented at different sampling rates, it can be asynchronous, there can be gaps in information, there can be occlusions from obstacles that cause all sorts of different errors in this knowledge of the correspondence of the A's and B's. And so we ask the question and are proposing a solution of how to calculate X in the AXXB problem without any prior knowledge of correspondence. We're saying correspondence exists, correspondence has to exist to solve AXXB, but we're saying we don't need to know that. We don't need to know to solve, which is something that we think is unique in the field. And so how do we do that? We need to leverage probability theory. And so I will go through some notation about probability theory and groups. So bear with me here through these wonderful definitions. Here we start very simply on Rn, and so we see that a probability density function is defined such that at all points the function is greater than 0, and that the mass of the function is equal to 1, the integral of the function. And the whole space over the integration measure is equal to 1. And so for this probability density function, of course, we can define a mean and covariance, and you can see these definitions here, very standard on this case of Rn. And we see that in the case of Rn, the convolution of two PDFs is very simply defined as the mean convolution of the means is the addition of the means, and the convolution of the covariances is the addition of the covariances. And in many of the, or in all of our cases here, we'll be working with a Gaussian density function, and so of course we can completely define a Gaussian by its mean and its covariance. So again, we're talking about the space of SE3, rigid body motions, and so we see what we saw before. We're talking about rotations and translations. Rotation can be parameterized by Euler angles, axis angle, whatever parameterization you want. So here you see the ZXZ Euler angles of the 3 by 3 Euler angles, and of course the three-dimensional translation vector. And on the Lie group, on SE3, there is a concept of integration. And here it is the definition of the integration on the Lie group. And this integration is natural, which is good for us. And what we mean by natural is that it is invariant to inversions and it is invariant to left and right shifts. And so what this allows us to do is define a convolution on SE3, on this Lie group. And here is the definition of the convolution, a definition of the convolution of two functions on the Lie group SE3. And some other notation that will become useful in the formulation of the problem is here we define a delta function where the integral over the Hart measure is equal to 1, and any shifts in the delta function are represented as such. So you can have the delta function spike at the origin and shift it to any element of SE3 through this definition here. And we'll also make use of that. Finally, just as a point of notation, we want to look at the V operator on SE3. And in the first talk, a lot was said about the manifold of SE3 and the tangent space of little SE3, the Lie algebra. And so this V operator is what allows us to look at elements of this Lie algebra, taking the basis vectors and their scalar multipliers and pulling out, so mapping SE3 to R6. So with all these definitions, we can now define a mean and covariance of the probability density function on SE3. And here you can see the definitions. M is now the representation, the matrix representation of the mean rigid body transform of a set of rigid body transforms of the probability distribution f of h. And so with these two definitions, we can leverage them into starting to look at the AXXB problem in a somewhat different light. Note here this log V operator, again, we're talking about this V operation. The log, of course, is the inverse exponential map, so taking elements from big SE3, the Lie group, into little SE3, the Lie algebra. And through this operation allows us to obtain a covariance. And we want to just make a note that these definitions of mean and covariance are a little bit different from what is standardly used in the literature for the Riemannian geometric approach, which the standard method is to minimize a function of the distances and retrieve the mean through that minimization. And we can think of the Riemannian distances, or the Riemannian distances are usually thought of as either something extrinsic or intrinsic, such as this equation here, or something extrinsic to the manifold here. The problem is for each of these definitions of distance, and for this definition of mean, the standard definition, there are properties that don't quite work in our favor. And we see that there are benefits to the previous definitions that we use over these definitions here. And we see that, one, we avoid the arbitrary choice of this weighting matrix here. Additionally, the mean behaves nicely under a convolution, which we'll see in a second. And the covariance of the mean remains under conjugation. So, for instance, the log of the conjugated mean is equal to the conjugation of the log of the mean. So now we want to take all this information and define this new method for solving Ax equals xb. So here we have one instance, one sensor measurement from each sensor, ai, x equals xbi. And so how we can phrase the problem now is as a problem of delta functions, or as a convolution of delta functions. And so we have delta ai, which again, remember, is the shifted delta function to ai, to that element of SE3, convolved with delta x equals delta x convolved with delta b, all shifted delta functions. And what this allows us to do is, unlike using elements of SE3, the rigid body transformations, and using these delta functions, we can now add these functions, and convolution is a linear operation. So all of these n instances can be written into a single equation. So these, we're talking about we need 2 or more sensor measurements to solve the AXXB problem. So now we can put all of these sensor measurements, all n of them, into single equations. And so we define our functions here as such, and basically it's the average of all of the delta functions of all of the sensor measurements. And so we have our equation here, which is now a convolution of f of a, all of the combined delta functions involved with x equals delta function x involved with f of b. And of course, we normalize these functions to be probability density functions in our space, which is what we need to do. So some assumptions of this problem is that given the set of A's and the set of B's as sensor measurements, and given some distance metric on space, we make the assumption, and it's a reasonable assumption, that these distances between A's and between B's are small. And if you remember back to the ultrasound motivation, the transformations we're dealing with are relative. They are small motions, one pose to the next. We're not looking at a pose from over here to a pose from over here. We're looking at small variations in the movement of the system. And so this assumption is valid for most of the types of applications that we're looking at. And so given this assumption, and why we need to make this assumption, is that we can now write the mean of 2 convolved functions and the covariance of 2 convolved functions in this form. And this, why there's this approximately equal, is that this gets more and more accurate, or more and more equal, as this condition is more satisfied. So as the covariances of these, as the covariances here become smaller and smaller. And so here the adjoint is defined as such, where again R is the rotation matrix, T is the translation vector, and this hat operator is given here. It's basically transforming the vector into a skew-symmetric matrix, and with a little bit of abusive notation here, we can say that the V of the hat of A is equal to A. So, since the mean of a delta function is, the shifted delta function is simply that amount that you shifted by, so a shifted delta function of x, the mean is equal to x, and its covariance is 0, it's just a spike. We can write our batch formulations using these different steps that we've talked about into these two equations here. And this is the crux of our solution formulation, or our method formulation, is we now have two AXXB equations given this probability theory framework. And so we have mean of A times X equals the X times the mean of B, and the adjoint of X inverse times the covariance of A times the adjoint transpose of X inverse is equal to the covariance of B. And remember, these covariances and these means are as defined previously, and not the traditional Riemann way. So if we look at these two equations and we ask how do we solve them? So we formulate the problem like, can you give me an answer for X? We can look at equation, we can start looking at equation 2, and we can decompose everything, all of these matrices into blocks. And so if we compose each of these elements into blocks as such, we can look at the first block and get an equation that relates the covariance of the mean of B to the covariance of the mean of A by the rotation component of X. And so we can see that we have the rotation component of X now somewhat isolated, and we want to ask, can we pull that out of this equation? And so we use an eigenvalue decomposition, and we say the sigma covariance is equal to here, where this is the eigenvalues on the diagonal, and the eigenvectors. And we can use this in our previous equation here to write this somewhat longer equation here, and then we condense, and we get this equation where the diagonal of the eigenvalues is equal to a conjugation of itself. And so by examining this formulation, we see that there are 4 possible solutions, and they are this set here, that these matrices could be to give this relationship. And so we go back to this problem, and we rearrange terms, and we say now that Rx is equal to this here, and so now we have four possible solutions of what our Rx could be. But we have lots more information from the other equations, and so we grab from one this notion of NMA equals Rx NMB, and N is the one of the geometric parameters of SE3, one of the Kluger coordinates, and it's simply the axis of the rotation of the element of SE3. And so from this mean equation, we get this relationship, and we simply choose one of the set of 4 from back here that minimizes this relationship. And from that, we can choose our Rx, or find the correct Rx. And then once we have Rx, it's somewhat trivial to find T of X. We take the second blocks from this equation, and then we solve for T of X. And so, of course, in our application, all of these sensor measurements are discrete. So we are dealing with going from the discrete world to probability distributions. So we can define the discrete mean and the discrete covariance as such. And we can use an iterative procedure for calculating the mean. Finding the mean is the more difficult part. So we start with initial guess of the mean, And then we use gradient descent to minimize this cost function, and that brings us closer and closer to the mean. And then once we have the mean, we can calculate the covariance as seen here. And so this then, with our set of sensor data, gives us the mean, or our sensor data gives us the mean and the covariance, which can then be plugged back into these equations and solved as was just discussed, and out we get the Rx and Tx for Rx, which, as we saw, Rx and Tx perfectly defines the element of SE3. And so, through this whole process, we've never had to use the notion of which A equals which B, which A is related to which B. We simply lump them all together in probability density function and solve. So we never have to deal with this notion of correspondence, which trips up pretty much all of the other methods that we've seen. And so here you see just a very simple plot. This Kronecker product method is just one of the many other AX equals XB solution methods. And so you see that under scrambling of the A and B sets, so basically with a loss of knowledge of the correspondence, the Kronecker product method, the typical method, begins to blow up in terms of noise, which makes sense. It's not made to handle that. But if you can see down on these lines here, our batch method retains zero error through any sort of scrambling of this kind of correspondence. So contributions, we've established the AXB sensor problem can be solved with the batch method, which I presented. It does not require a priori knowledge of A-B correspondence. We showed that the formulation, or we showed the formulation and solution of this batch method, and we showed that the batch method can be used to solve for X given any sort of lack of knowledge of the correspondence and sort of scrambling in the AI to BI relationship. And so where do we want to go? We look to continue to optimize for the noise case, noise above and beyond the loss of correspondence, so these other two constraints that I mentioned earlier. And we want to continue to test with experimental data. So we have the ultrasound experiments, we want to continue to look into that, but also into other applications as well, and combined with additional data processing algorithms that we're looking at to solve this problem. So this work was supported by the NSF, and I want to thank the organizers of GSI,